is the Transmission Electron Microscope, or TEM, which is used to take images of structures that are inside materials, much like an X-ray machine takes pictures of the bones inside our bodies. For example, TEMs are used to take the pictures of these sections of a transistor. However, in other domains of science, TEMs can be used to take images of proteins inside mitochondria, the powerhouse of the cell, or of nanoparticles of pure gold. Transmission electron microscopes are typically more complex than SEMs and have a resolution up to 50 picometers, which is roughly the size of a hydrogen atom. One quick note is that TEM is that it generates electrons and accelerates them to around 70% the speed of light, thus creating a beam of electrons. Next, a series of magnetic lenses focuses the electrons down to a small area and shoots or transmits these electrons through the specimen that we're looking at. Depending on the different densities and materials inside the specimen, the electrons are scattered as they pass through it, thereby imprinting an image of what's inside the specimen onto the beam of electrons. The imprinted beam of electrons is then magnified 40 times using an objective lens, and further magnified 50,000 times using a set of projector lenses. At this point, the imprinted image is 5 or so centimeters wide and large enough to be captured by a high-resolution camera sensor at the bottom of the microscope. We'll explore the detailed engineering in a little bit, but for now, you might be wondering, why do we have to go through the hassle of manipulating electrons, and why can't we just use light? Well, visible light is physically limited to magnifications up to around 2,000 times, and if you try to zoom in further, the image remains blurred without revealing any more details. On the other hand, electrons can reach meaningful magnifications up to 2 million times. Why then is light physically limited? Well, let's return to this image of the European peacock butterfly and the scales on its wings. This image was captured with a camera. This image was taken with a light microscope. And these images were captured with an electron microscope. Let's consider two features from the specimen that are only 100 nanometers apart. Visible light has an average wavelength of 540 nanometers, which is larger than the distance between these 2 points. Due to the physics of waves, as light hits these two features, it's bent around, thus creating a pair of propagating waves with a diffraction pattern resulting from the interference of the two waves. If the features are substantially closer than the wavelength of visible light, then the diffraction pattern will make the two features appear like a single blurred feature. In short, visible light can't really resolve features that are less than 300 nanometers apart. However, in this electron microscope, electrons are accelerated to 70% of the speed of light and have a wavelength of 2.5 picometers, which is around 200,000 times smaller than visible light's wavelength. In principle, such an electron microscope could resolve features spaced just 1 picometer apart. But due to the magnetic lens's physical limitations, the real resolution is around 50 picometers, which is enough to see individual atoms in a material. Also, if you're wondering about the scale of micrometers, nanometers, and picometers, here's a comparison of the size of each unit. Let's now dive into the complex science and engineering behind each part of this transmission electron microscope. We'll begin at the top with a device called a field emission source, which generates free electrons. The basic principle is that negatively charged electrons are attracted to positive electric fields. Here we have a tungsten crystal needle, and below is a ring called the extractor. This extraction ring is connected to positive 5,000 volts. And as a result, the negatively charged electrons in the tungsten are pulled towards the extractor. The electric field's effect on the electrons is amplified by the sharply pointed tungsten crystal, which is only a few nanometers wide, and as a result, the electrons are freed from the tungsten. The next step is to accelerate them to 70% the speed of light. To do this, we use a series of metal rings which are graduated to be tens of thousands of volts apart from one another. And just like before, these positively charged rings use electrostatics to attract the negatively charged electrons, which are accelerated through the center of the rings. There are two key reasons for the incredible speed of the electron. First is so they can travel through the specimen, whether it be a transistor, protein, or a crystal lattice, or something else that has been sliced to typically only 100 nanometers in thickness. And second, as mentioned earlier, electrons exhibit wave-like properties, and the faster they are, the shorter the wavelength and the higher the resolution achievable. One important detail is that when the microscope is running and electrons are being accelerated to relativistic speeds, vacuum pumps are used to remove all the atmospheric molecules, thus creating a vacuum similar to the vacuum of outer space. This is because incredibly fast-moving electrons will scatter in random directions as they collide with air molecules and thus ruin the images of the specimen. Now that we have a beam of electrons, we'll explore the magnetic lenses, of which there are essentially three sets: the condenser, the objective, and the projector. The role of the condenser magnetic lenses is to focus the electrons from the source and project them onto the sample, so that they illuminate an area the size of a micrometer to several nanometers, depending on the desired magnification. Additionally, the microscope uses apertures, or holes, placed in the path of the beam to filter out any electrons that are fanning too far from the center of the column, or optical axis, resulting in electrons more parallel to one another before they hit the specimen. The specimen is placed on a holder which is inserted through an airlock into the vacuum chamber. To see different aspects of the specimen, such as the crystal lattices, the holder can move or translate the specimen in all three directions, X, Y, and Z, and rotate the specimen along the X-axis, and with some holders, also the Y-axis. With this, we can get images exactly perpendicular to the features, such as these transistors inside. The incredibly small beam then hits the specimen composed of different elements and densities of materials, thus scattering the electrons in different ways, thereby imprinting an image on the transmitted electron beam. The next lenses, the objective and a series of 4 projector lenses, are used to resolve and magnify the minuscule image imprinted into the electron beam up to a width of a few centimeters. This process is separated into 2 parts. First, the objective lens, often considered the heart of the microscope, magnifies the image by 40 times, and its optical aberrations define the final resolution. Then the projector lenses magnify the image the rest of the way by 50,000 times. What are optical aberrations, and why is 2 million times the typical maximum magnification? Well, let's look at this image of 962 blurry atoms of gold. With today's technology, the TEM's ability to resolve the smallest features is not limited by the electrons in the beam, but rather by the lenses and the aberrations and distortions that they add to the image-imprinted electron beam after it's been magnified. There are a few main types of aberrations, such as spherical and chromatic, which we won't explore further. But the main idea is that perfectly controlling a beam of electrons is far from trivial, and the aberrations add blurriness and impede resolution after the magnification. The projector lenses magnify what has already been magnified by the objective lens, including the added aberrations, and this second magnification adds its own aberrations afterwards. Therefore, a considerable amount of science and engineering is dedicated to reducing the aberrations introduced by the objective lens, as that is what ultimately limits the sub-nanometer scale resolution of the microscope. One thing you're probably wondering is why these magnetic lenses look nothing like microscope or camera lenses, and how do magnetic lenses operate on fast-moving electrons? Well, inside the lens is a coil of copper wire surrounded by an iron housing. When a current is run through these coils, a magnetic field is produced. This magnetic field is then routed through the iron to the pole pieces, where it's channeled into an optical column. These magnetic fields are then used to change the trajectory of the electron by bending the electrons toward the center, or optical axis, in a shrinking helical direction. The physics at play is the Lorentz law. To summarize, the force on the electron is equal to its charge, Q, times v, or the electron's velocity vector, crossed with b, the magnetic field vector. In short, if the electron were to have a velocity away from the optical axis, it would be forced by the magnetic field down towards the center. However, if the electron were traveling perfectly down the center along the optical axis, it wouldn't experience any Lorentz force from the magnetic fields and would just continue down the center. As a result, the magnetic lenses act as convex or converging lenses, focusing all the electrons down to a focal point. As the electrons continue their trajectory past the focal point and expand, they produce a magnified image. This magnification depends on the strength of the magnetic fields, the position of the lenses, and the position of the detectors and cameras. Let's move further down the microscope and explore how we turn electrons into images. There are two separate systems. First, we have a phosphorescent screen, which has a special coating that glows when electrons hit it, and a camera is used to view the screen. This system is used to align the microscope and provide an overview of the specimen. When you're ready to capture a high-resolution image, the phosphorescent screen moves out of the way, and the image is captured using the second system with a more sensitive CMOS camera that has a higher resolution and dynamic range. The purpose of having two systems is that the phosphorescent screen and camera is used to ensure that the electron beam and magnetic lenses are set up properly, as an incorrectly focused beam could damage the sensitive CMOS camera. We've covered many key parts of the microscope, but there are other pieces of equipment and modules that provide additional features. For example, there are X-ray detectors, energy filters, phase plates, monochromators, multiple correctors, mechanisms to hold and adjust apertures, water cooling for the magnetic lenses, tons of circuitry to control the magnetic lenses and the field emission source, vacuum pumps, power supplies, and much more. Additionally, the entire microscope sits on air cushions to remove external vibrations.